Hello everyone. So today is our last video on 6.3. So the last example I want to show you is the following. Notice that whenever you have multiple dependent variables in this type of questions, you always wind up solving a system of equation. And the system of equation that you solve is actually a linear system of equation, just like what we have learned in chapter 2. And therefore offer us some unique way to actually come up with a solution to that system. And one way is to use matrix method. Hopefully you remember how what we learned in chapter 2, where if you have a system of a system of linear equations, you can always rewrite that into a matrix equation. And then once you're in a matrix equation, you can actually use the inverse matrix to solve the system, provided that the inverse matrix exists. Now for us, we do hope that the inverse matrix exists because we are looking for a unique solution to our system. So therefore, if we can rewrite our partial derivative equation into some kind of system of equation in matrix form, then we'll make solving it a lot easier to do. So that will be what today's example is going to be. And that is the last example that I want to do with you in 6.3. So today's video could be relatively short, which would be a good thing, I think. So let's try let's go through the example and see. So let's say we're given the following equation. So in this case, we're going to have three equations because we're going to have three dependent variables. So the equation will be xu plus yv plus zw is equal to 1. X plus y plus z plus u plus v plus w equal to 0. And xy plus zuv plus w equal to 1. And here's the important sentence. Remember, assume that x, y, z are functions of u, v, v, w. So therefore we define x, y, z as dependent variable. U, v, w are our independent variable. Here's what the question asks you to do. Find a matrix equation that can be used to solve for the partial derivative of x, y, z with respect to let's say w. So essentially what I'm looking for would be dx over dw, dy over dw, and dc over dw, but not actually what those derivatives are, but rather a matrix equation that can solve for those three things. So what does that mean is that we are basically treating dx over dw, dy over dw, and dc over dw as the variable that we're looking for, the answer that we're looking for. And we try to form a coefficient matrix and a right side matrix along with those three partial derivatives that will allow us to come up with a solution to them. Okay, so and I'll show you how that's being used also in once we finish the problem, and show you what would be the next step. Okay, or maybe we'll do this as A then. Okay, so let's go for it. So let's see. So we want it to be respect to w. So therefore what I'm going to do is I'm going to take each of these equations, xu plus yv plus zw equal to 1. I'm going to basically take the derivative of this thing with respect to w and see what we got. So nothing but to go for it. So xu, what is the derivative of xu with respect to w? So in this case, remember u, v, w are independent variables. So therefore u in this case, u is an independent variable, therefore it's considered to be a constant. So therefore we literally just taking derivative of x and multiply by u. So therefore become u dx over dw plus yv, when I take the derivative of that, same thing happened. V is another independent variable, therefore considered to be a constant. And so we're basically differentiating y with respect to w, so therefore become dy over dw, so become v dy over dw. Plus, now this one is tricky, zw, because z is a function of w, and so is w itself. So therefore, it becomes a product between two things that involve w, and therefore product rule now need to be applied. So therefore it becomes z times the derivative of w, which is 1, plus w times the derivative of z with w, which is dz over dw. And that's equal to 0 because the derivative of 1 is 0. Now, to put the equation into proper form, this is what I'm going to ask you to do. I'm going to basically line up the partial derivative in order, meaning dx dw, dy dw, dz dw, and then leave anything else on the other side of the equation. So therefore, I'm going to rewrite this into u dx over dw plus v dy over dw plus w dz over dw equal to, and then we'll move the z to the other side, become negative z. All right. So now it's just a matter of do the other two equations. So let's go for it. So d over dw of the second equation, which is x plus y plus z plus u plus v plus w equal to 0. All right. So how will we do this one? Well, same way. I'm just going to basically take the derivative of all of them. So let's start. So derivative of x with respect to w would be just dx over dw. And plus dy over dw plus dz over dw plus u is an independent variable, so therefore when I take the derivative, that becomes 0. V is also another independent variable, so therefore that also becomes 0. And then w, when I differentiate with w, that becomes 1. Equal to derivative of 0 is obviously 0, so therefore it's 0 on the other side. And so therefore this come out to be, I'm going to do the same thing, dx over dw plus dy over dw plus dz over dw equal to negative 1. Now let's do the third one. So d over dw of the third equation, which is xy plus zuv plus w equal to 1. So when I take the derivative with respect to w of xy, that becomes a problem because x and y are both function of w. So therefore, product rule need to be applied. And the product rule dictate that this will equal to x dy over dw plus y dx over dw plus zuv. uv are both considered to be constant in terms of when we differentiate with w. Z is a function of w, so therefore we do need the derivative of that. So therefore it just becomes uv dz over dw plus the derivative of w is 1 equal to the derivative of 1 is 0. So therefore now what I'm going to do is I'm going to rearrange it and put it in order. So I'm going to go and put down y dx dw first because I want dx dw first, plus x dy dw plus uv dz over dw equal to negative 1. And so now I have these three equations. So now just a matter of trying to put it into a matrix form. So to do that, what I'm going to do is simply line them up and then identify my coefficient matrix and my right side matrix. And it's actually pretty simple. So what I'm going to do is now put these three equations together. So therefore, if I combine these three equations together, I'll have u dx dw plus v dy dw plus w dz dw equal to negative z. My second equation say dx dw plus dy dw plus dz dw equal to negative 1. My last equation said y dx dw plus x dy dw plus uv dz dw equal to negative 1. So notice that basically lining up the dx dw, dy dw, dz dw, just like I would line up with x, y, and z. Okay, and now I can transform this system of equation into a matrix form. So what is the matrix form? Matrix form is actually referred to this form. A vector x equal to vector b, where A is our coefficient matrix, vector x is our variable vector, and then vector b is our right side vector. So what is this whole thing turn into? Well, actually turn into this. We just simply collect the coefficient and just put them the position where they appear on the system. So u, v, w. And the coefficient for the second equation is 1, 1, and 1. And then for the last equation is y, x, u, v. Here's my vector x, or the variable vector, which in this case are the three partial derivative. And yes, you do have to write them vertically. Equal to the right side vector, which is vector b, and that would be, so that is the answer that you were looking for. Ax equal to b. A vector x equal to vector b. Now, what if I ask you to solve for this? Then how would you go about doing that? Well, because of the fact that we have a matrix, then we can actually solve for it by simply do the following. So part B, so maybe not part B. I mean, I don't really anticipate actually asking you to do this, but I do want to kind of talk about it since now that we have the topic. So note, we can now find the three partial derivative in this case. In this case, dx dw, dy dw, and dz dw using an inverse matrix. What do I mean by that? Meaning that now I can say dx over dw, dy over dw, dz over dw would technically equal to the coefficient matrix UVW 1, 1, 1, y, x, uv, inverse multiplied by negative z, negative 1, negative 1. So that becomes what the partial derivative equal to. Now, obviously, you might be thinking, well, how are we going to find this inverse with u, v, w, and x and y, all of them inside? Well, you're not finding that inverse derivative the way it is, but once we put in numbers for them, then we'll be able to do it, okay? So in this case, maybe we can do the following. The important part is that we just have to make sure that we do have an inverse, and otherwise we won't be able to do this process. All right. So obviously we can't find the inverse with all the variables involved, but what if I ask for the following? Imagine I ask for the following. I'm going to ask you to find dx dw, dy dw, dz dw at let's say UVW equal to 1, 0, negative 1, and let's say XYZ is equal to maybe 1, 1, negative 1. And now plugging those numbers will now allow us to actually have our derivative, our coefficient matrix, and our right side matrix, our right side vector, all become just numbers, and therefore now allow us to actually finish the problem and find our partial derivative at that particular moment. So therefore it becomes this, dx over dw. Okay, let's see. Dy over dw, dz over dw would equal to u, which is 1, v, which is 0, w is negative 1, 1, 1, 1. Y is 1, x is 1, uv would be 1 times 0, which would be 0. Inverse multiplied by negative z, which is 1, negative 1, negative 1. So now just a matter of trying to figure this out. So now the key is obviously finding this inverse. So if you remember how to find the inverse from chapter 2, you can definitely go for it. If you don't, your calculator can actually do that. So finding the inverse is not what I want to focus on. I'm going to just assume that you either calculate by hand or have a calculator. So I'm going to put into my calculator to see what the inverse look like. So let me see. So therefore, this come out to be this matrix. The inverse of 1, 0, negative 1, 1, 1, 1, 1, 1, 0 is actually 1, 1, negative 1, negative 1, negative 1, 2, 0, 1, negative 1, multiplied by 1, negative 1, 1. And then now you can just simply do your matrix multiplication. Or if you want to, you can type into a calculator and do that. Oh, I forgot a negative 1 right here. So if you simply multiply this out, let's see, that would be 1 minus 1 plus 1. So top number would be 1. And then we negative 1 plus 1 minus 2. So the middle number is negative 2. And then 0 minus 1 plus 1. So that's 0 on the bottom. So therefore, that tells me that dx over dw equal to 1. dy over dw equal to negative 2. And dz over dw is equal to 0. That's my partial derivative at this moment right here. So on your next test, you will be asked to do something similar to this, where you have to form the matrix equation. I highly unlikely ask you to actually go through the process to find this answer at the end, because that will require you to do an inverse matrix that might be 2 by 2, which will be okay, but if it's 3 by 3 or higher, it will become a lot more work that I don't intend to ask you. So therefore, most likely what you need to be able to do on your next test is up to this step where you form the matrix equation, and that will be it. But this is the reason why we want the matrix equation, because we can then plug in numbers and then find the inverse of the matrix and then solve for the solution. All right, I think that's all that is for 6.3. So we'll talk to you again soon. Okay, bye-bye.